Yeah, yeah.
So, hello everyone. Thank you for joining. So, we'll be starting in 1 minute. So, Kushal, are you there?
Yeah,
Kushal?
yeah. Can you hear me? Sagar, can you hear me?
Can you hear us, Sagar?
Yeah, yeah.
So hello guys, can you hear me now? Hello.
Yes, we can hear you.
Okay. So guys, so here you can see our universe in a small scale. So ever wondered why our universe is luminous and colorful? In this image, we can see many celestial objects which are emitting radiation, which are electromagnetic radiation, like they are blue colors, orange, red, yellow, green, so many colors. So why are objects emitting different wavelengths of light? And I also have some images of stars which mention the surface temperature of them. So here we have Zeta Ophiuchi, which is 34,000 Kelvin. Its surface temperature is 34,000 Kelvin. And Spica, its surface temperature is 23,000 Kelvin. And Rigel, 11,000 Kelvin. So, and Sirius is 10,000 Kelvin. Now, in all these stars, you notice that they have blue tinge. That is, they are blue in color. And now there is Vega. So in Vega, the temperature is 9,600, which is white in color. And Sun is yellow in color, where its temperature is 5,800 Kelvin.
Excuse me.
Sagar, are you there?
Hey, Kushal, could you take over? I don't know where Sagar is.
I think I can share the screen and we can take it over.
Okay.
Aditya, can you share the screen?
Sure, bro. 1 second.
And start with your part.
One second. You guys can hear me, right?
Yeah, we can.
Okay, wait, who's sharing the screen right now?
I think it's Sagar again.
Somebody already sharing the screen.
Is it Sagar?
No, I don't have permission to share some media on that presentation, so I can't present it. I think only Sagar has access. We need him.
So hello guys, can you hear me?
Yeah,
Yeah,
bro.
perfect.
Yeah, even I can hear you. Sorry everybody, there was a lag and huge internet issue in my side. Okay, so I'll
Can
be
you restart from the
continuing.
beginning?
Yeah, sure.
Okay.
Just a minute. Okay. So our topic for today is application of quantum mechanics in astronomy. So the first application is, so we can see here the various luminous objects in our galaxy in a small case, in our universe in a small scale. So we can see red stars, green stars, orange, yellow, blue, so many types of stars. Now ever wondered why these objects are having different spectral emissions, like they're emitting different radiations? So why is that? And I also have some images of stars. So the first is Zeta Ophiuchi, which is having 34,000 Kelvin, and it's slightly indigo in color. Its color is slightly bluish. And then it's Pika with 23,000 Kelvin, which is also blue. And then we have Rigel, 11,000 Kelvin, and it's slightly dark blue or slightly indigoish blue still. And then Sirius, now its surface temperature is 10,000 Kelvin, and the frequency, like we can say that the blue has been little reduced. And then comes Vega with 9,600 Kelvin, which is slightly white with very small bluish tinge. And then the Sun with 5,800 Kelvin, which is yellow in color. And Arcturus star, which is 4,300 Kelvin, its surface temperature is 4,300 Kelvin, and its color is slightly orangish red. And then we have UY's QT with 3,400 Kelvin, which is red in color. So if you had noticed, as the temperature of the stars decreased, their color also changed, such that the wavelength of the light they emitted increased. So we can say that as the wavelength of radiation emitted by objects is inversely proportional to their temperature, right? See, initially it was 33,000 Kelvin, where the temperature was dark blue and slightly indigo. And then as the temperature came to 3,400 Kelvin, then the color became red. So as the temperature increased, the wavelength of the radiation which was emitted by stars decreased. So we can say that the lambda, that is the wavelength of radiation emitted by the stars, is inversely proportional to the absolute temperature. So now why is this happening? So what is the reason for this behavior? So that is got by Planck's distribution law. So Planck's distribution law is applicable to black bodies mainly. That is those objects which can absorb and emit radiation of all frequencies uniformly. So so we assume here that stars is also approximately like black bodies, and they also radiate electromagnetic waves. So Planck said that surface of the stars is considered to be made of particles which can oscillate about their mean position and which are also coupled to each other. So you can see in this image that there are some atoms which are coupled to each other, and so this is how the star surface is made to be according to Planck, and they vibrate like this. So the surface will be vibrating, oscillating in this manner in black bodies. So okay then. So then an important property of these particles is, since they're very small, uh, they actually come to the quantum realm, and they occupy these discrete energy levels. So here you can see that the discrete energy levels which are occupied by these quantum oscillators. So these particles are called as quantum oscillators because they occupy discrete energy levels, which is given by E is equals to n plus 1 by 2 h nu. So these are the only levels which are occupied by these particles. So when Planck used quantum statistics by considering the number of particles and many other features, what he gave is, he gave an equation called E lambda is equals to 2hc square by lambda power 5 into 1 by e power hc by lambda kt minus 1. So this is the famous equation called as energy distribution equation, which relates the spectral density of a particular wavelength lambda at a particular temperature T. So where h is the Planck's constant, c is the speed of light, k is the Boltzmann's constant, and if you plot a graph between the spectral energy density of a particular wavelength, that is E lambda, and the wavelength of electromagnetic radiation, we get an interesting curve actually. So here you can see that how the energy density varies as the lambda changes at a particular temperature. So here you can see that initially, consider a particular temperature like 4000 Kelvin. Initially, the spectral density for smaller wavelengths is very low, and even for larger wavelengths is very low. But for particular temperatures, like so for particular wavelengths, like for 4000 it is like 700 nanometers, and for 4500 it is like 600 nanometers. So at a particular temperature for a particular wavelength, the spectral density is very high. So that is because of this equation called as lambda max is equals to b by t. So this equation is also derived from Planck's distribution law itself, called as Wien's displacement equation, which relates the lambda max, that is the max, the wavelength where the spectral energy is maximum, that wavelength it relates with temperature, that absolute temperature of the black body. So so by this relation, we already have seen in stars that as the temperature increases, the wavelength decreases, and moreover, and so since this happens, we get an important result from this. So now, what is important is it helps us to calculate the temperature of most of the celestial objects. Like, see, in our universe there are many distant objects where we can't go actually and measure the temperature. Then how will the temperature of such objects will be calculated? It's because of this equation, Planck's distribution equation, where they measure the maximum wavelength, that is the radiation whose spectral density is highest, and they measure it and they relate it with this equation and find out the temperature of that object. So this is how they measure the temperature of distant celestial objects. So this is an important application of quantum mechanics in astronomy. So if we come to the next application, here in this table you can see some elements like hydrogen, helium, oxygen, and their percentage is actually the percentage of elements in our own sun. Like they say that hydrogen is 91% of atoms in sun is hydrogen, and 8.7% of atoms in our sun is helium, and we got a table which gives the list of elements and the abundance of those elements. So did you wonder how this is actually calculated? So and here we can see that in this image, this is actually the core of our sun, which shows the different fusion levels. Like the outermost fusion level is hydrogen fusion, and then comes the carbon, and then comes helium, and then carbon and oxygen. So like this it goes till iron. So the core of our sun is having so many fusion shells in it. So how are this information got? Now the sun is 150 million kilometers away. Then we need some instrument or something which can or some method which we can find out the number of list of elements in it, right? So that is got by spectroscopy. So in spectroscopy, actually it says that every property, every element has a unique number of spectral lines. So it's actually like this. So consider hydrogen. So if we make hydrogen to emit spectral lines, then it will be only these wavelengths. Like it, see the hydrogen, actually there are some electron transitions happening in hydrogen. The first transition corresponds to this red wavelength, and then comes blue, and then it goes till indigo and violet. So we can see that this set of spectral lines at this particular level, that is the particular wavelength, is given only by hydrogen. No other element has this same spectral lines. Similarly, you can see here, sodium has only 2 spectral lines in yellow, and then helium has some spectral lines in different levels. And you can see that no spectral line matches. And here you can see the spectral lines of some other elements like carbon, nitrogen, oxygen, and iron. Here also you can see that even though you can see in oxygen and iron the purple, that is the higher frequency, higher wavelength, the higher frequency wavelength, the spectral lines they match.
Are you speaking, Sagar?
Sagar, we can't hear you.
So the first, can you hear me, guys?
Yeah, we can hear you now. Can you go to the previous slide again?
This one.
Just the latter half.
Okay. So, okay. Now I was telling about oxygen and iron. So we can see that though many spectral lines of oxygen and iron in the shorter wavelength they match, they're not the same because the longer wavelength, that is the red wavelengths, are not matching. So this is how we can distinguish two elements like oxygen and iron. Now, if you want to know more about the mechanism of spectral lines, you have to know two things. That is the Maxwell's picture of light. That is where Maxwell told that light is made up of electric and magnetic field which are oscillating perpendicular to each other, and they have wavelengths and frequencies and so many things. So now if we know this wave picture, and then Planck, he also showed the particle picture of light. That is light is made of, that is the light is made up of photons having discrete energies called as h nu, and it's also equal to hc by lambda. So these two pictures show the dual nature of light, and this is used in the spectral lines in that concept. So how is that, we'll see. So here you can see the energy level of hydrogen like atom, where there are many energy levels like 1s, 2s, 2p, 3s, 3p. So these are the energy levels of hydrogen-like atoms. Now, when the electrons get heat, when the electrons get heat energy or light energy or any other form of energy, if they absorb, they go to higher energy levels by absorbing the energy difference. So this is how electrons goes to higher energy level. Now, what happens if the electrons come to lower energy level? That is, if the electron come from some initial level energy level EI to final energy level EF, then they have to emit some photon which corresponds to the energy equal to the energy difference between them. So delta E is the energy which will be carried by those photons, which is equal to EF minus EI, which is also equal to the photon emitted by that electron transition, that is hc by lambda. So delta E is hc by lambda. So we can equate these two equations and we get hc by lambda is equals to EF minus EI. Now, by using Schrodinger's equation for hydrogen-like atoms, the energy eigenvalues, that is En, was found out. So at a particular energy level En, the energy value was this, which says En is equals to minus z square m e power 4 divided by 8 h square epsilon naught square n square. So these are the energy values of hydrogen-like atoms. So for first level, that is n is equals to 1, we get one energy level. For n is equals to 2, we get another energy level. So like this, we can give the set of energy levels for hydrogen-like atoms. Now, if we apply this to the previous equation, that is EF is equals to z square me power 4 8h square epsilon naught square n I square, and EF is equals to z square me power 4 8h square epsilon naught square n f square, then we get this equation, that is hc by lambda is equals to z square me power 4 8h square epsilon naught square into this factor. So now we get the, so by this equation we can simplify more and get the value of wavelength, right? So 1 by lambda is equals to this quantity. So if we know the proton number, that is the Z, and mass of electron and charge of electron E, Planck's constant H, epsilon naught, which is the permittivity of free space, and C is the speed of light, and NF is the final energy level and Ni is the initial energy level. If we know this, then we can calculate the wavelength, right? So by this we can calculate the wavelength. Actually it's the 1 by lambda, that is the inverse of wavelength, but still if we take the reciprocal we get the wavelength. So if we do this for different if we actually solve this for Z, that is the atomic number, we get this equation. Now how does this help in studying objects, that is the celestial objects? So consider we are getting a light source from some celestial objects which is having this spectral lines. Okay, so there is a spectral line coming at 670 nanometers, and another spectral line coming from 485 nanometers, and another from 420 nanometers. So like this, they are getting some spectral lines from some object, you think. Then what the scientists do is they match the spectral lines using that wavelength, and they do trial and error with the energy level, that is the NF and NI, and they do it such that the value of Z what they get has to be constant. So if they do this and if they get the value of Z to be constant, then they can finally say that this source was got from, this light source was got from this element. So this is how astronomers or scientists, what they do is they find out the content or the matter what is present in some distant celestial objects. So consider there is some nebula which is emitting some radiation to us. So what they do is they put a prism and they get the spectral lines, and they calculate the atomic number, and then they what they do is they find out that this element is present in that nebula. So this is how spectroscopy helps in finding the content of the element present in some distant objects. So this is an important application of quantum mechanics in astronomy. Now Aditya will be presenting more about his topic. So Aditya, you can continue.
Hey guys, thank you Sagar for a very informative, presentation. So what I'm going to be talking about mainly is the life of a star, or rather the death of the star, the life of the star towards its very end, and the factors that determine what a star is going to become, like after it dies, right? Towards the death of a star. So there's one governing equation that basically explains or controls all of stellar evolution. Sagar, can you go to the next slide, please? So this is called the equation of hydrostatic equilibrium. So in essence, a star always has two forces acting in opposite directions. One is the self gravity, that is gravity due to its own mass, that is trying to pull itself to collapse to the center, and there's an internal pressure. So this internal pressure in most of the main sequence or regular stars is due to nuclear reactions that are happening in the core. Kushal is going to talk more about this later. But mainly the thing to note here is that it's a very delicate balance. So there's going to be nuclear fuel burn, which is hydrogen, which keeps getting combined to helium, and this releases energy and pressure, and this is what sustains a star. If it were not for this, then the gravity of it would eventually make it collapse to the center. So because it's an equal and opposite, two different forces are acting, and it's stable, hence it's called equilibrium. And the dp in this equation, what you see is the difference in pressure, and that is what governs the entire thing. So what happens throughout a star's life? Saga, next slide please. So when it runs out of nuclear fuel, it can end in two ways depending on the mass of a star. So now our sun is a relatively light star in the cosmos. So such light stars, after their main sequence stars are basically ones that are still burning hydrogen to generate energy and light and heat. So once its fuel is running out, lighter stars become something that's called as a red giant. So a red giant is, so when hydrogen is burning and it runs out of fuel, it's going to start burning helium now, and the star is going to collapse because it does not have as much stability as it did when hydrogen was burning, because hydrogen releases more energy. But after helium, it's going to start burning carbon, and at this time, the energy is actually way more. Energy release is way more than it was during the hydrogen cycle. This causes the outer layers of the star to expand, or rather the entire star, except for the core, is going to expand to form a red giant. Sagar, can you go to the next slide, please? So this is how a red giant looks like. And what happens is after it, finishes running that fuel as well, it's like it can't keep, it does not have an infinite amount of matter to, keep burning and keep churning pressure for externally. So what happens after this? Core of the star, which contains the main reactants for the nuclear reactions that are happening, remains, but the outer layers just kind of fade off, to form a planetary nebula. Now this name is misleading because this neither gives birth to stars nor does it give birth to planets. It's just that when it was first discovered in like the 19th century, it looked like a planet, like how they had just seen Neptune, they just discovered Neptune, and they saw something in the sky in the Milky Way, and they were like, "Oh look, it could be a planet," but it's actually just a nebula because it's a cluster of hot gas surrounding a star. But yeah, that's the reason it's given a planetary nebula. So you have the outer layers just fade off to form a planetary nebula. Now this is very important because this contains the heavier particles, like the ions and stuff that get thrown out across the cosmos later, that could sustain life. And but the core of it, if it's a light sun, if it's a light star, the core of it collapses to form something called a white dwarf. It's a stellar remnant. Saga, next slide please. So this is a white dwarf, and I will be going into detail about what keeps this stable, because I just told you that all the nuclear fuel has run out. So what's stopping gravity from collapsing in this case? But here we see Sirius B. It's the small, you can see in the arrow mark, it's a small thing in the binary system, Sirius A and B. Sirius A is like a main sequence star, and Sirius B is a white dwarf. This is the closest white dwarf to us right now. Now, white dwarfs are the most stable. I'll tell you why that is. Theoretically, it could end into something called a black dwarf. We have not discovered a black dwarf yet, but it just says, in tens of hundreds of billions of years, we could find a black dwarf if, that's what a white dwarf would turn into. Okay, Saga, next slide, please. So now what if it's a heavier star, right? If it's way heavier than the sun. So this is going to form something called a red supergiant. Like the example that he gave of Betelgeuse is a red supergiant. This naturally has more mass, so it's going to be bigger, and it's going to be its main characteristic about everything is basically it has a higher mass. I bet everybody's heard of supernovae. So a red supergiant, when it's done fusing, when it's finished its nuclear reactions, some of the mass leaks into the core. Leaks would be more like the gravity of the core, because it has a higher mass, is enough to pull some substance from the outer layers of the star itself. So this results in an extreme release of energy. This is what we see as a supernova. This just blasts, light, radiation, matter just all across the universe in a spectacular blow that we see. This is also very interesting because we can, just like a planetary nebula or any nebula, using spectroscopy, like how Sagar had told, we can find the elements that are there inside a supernova, and we can see up to what stage a star has come in building up its nuclear reactions. There's hydrogen, helium, carbon, oxygen, all the way up to iron, because iron is the most stable element. So this supernova will result in either a neutron star or a black hole, because the mass is so much that the mechanism by which a white dwarf remains stable, it just won't work anymore, because the gravity is going to overcome the internal pressure. Saga, next slide, please. Yeah, you can see this is an example of a supernova, and in the next slide you'll see neutron star and black hole. You will have a there's going to be a bunch of black hole images everywhere, so I've just taken the actual black hole image instead of a cool looking one that you find on the internet. But I mean, this is pretty cool. Neutron stars, they're usually very rapidly spinning, so and they have charged particles, so these form a magnetic moments, and so their magnetic moment is actually pretty high. So those magnetic field lines are very strong. It's the strongest among every star. If it gets beyond the range, it's even called a magnetar. But that's another topic. That's for astrophysics. Okay. So to explain, next slide, please. So to explain the stability of the white dwarf or a neutron star, we need to get into two topics related to quantum mechanics. One is mainly particle physics, but still, it's the standard model of particle physics. This is almost like the periodic table, but for fundamental particles. So periodic table has different elements, atoms of different elements with their masses and whatnot, but these are fundamental particles. This is not made up of anything else. So all you need to know is all matter is made up of, or rather what we know is made up of protons, neutrons, and electrons. And protons and neutrons are further made up of quarks. There's something called quarks. These are fermions. So fermions are basically particles which follow Fermi-Dirac statistics. In other words, they have half integer spin. They have plus or minus half. That's usually what you categorize as fermion. And electrons also fermion. It has a plus half spin. So a proton and a neutron, they're made up of quarks. So a proton is made up of 2 up quarks, and neutron is made up of a down quark and 2 up quarks. An up quark has a charge of plus 2/3, and a down quark has a charge of minus 1/3. So a proton, you can see if there's 2 ups and 1 down, it's going to be 2 plus 2 minus 1, which is 3/3. So it's going to be 1 plus 1 charge. And a neutron is 2 down, so minus 1 plus 2 is going to be 0. It's going to be neutral. So there's something called a weak force that talks about changing the flavor of a quark. That's what its main function is. That is carried out by the W and Z bosons, which I will get into when I talk about neutron stars. So the thing about fermions is they follow something called the exclusion principle. Saga, next slide, please. So yeah, these are the baryons that I was talking about. This is a proton and this is a neutron. You can see how it's there. And another cool thing is the main thing about weak force is it deals with the changing of quarks and every and all radioactive decay and nuclear reactions. So basically, what one of the reactions is a down quark is an up quark converting to a down quark. That is through the W plus boson. Saga, next slide, please. So the Pauli exclusion principle that I was talking about for fermions, many people would have learned it in high school as saying, or PU college saying, it's impossible for any two electrons of an atom to have the same values of all four quantum numbers. This is actually a specific case. A far more generalization would be no two fermions can occupy the same quantum state. Can occupy the same, all the same quantum states. This is because fermions, which have half initial spins, when you have a multiple of them as a group, their wave functions tend to be anti-symmetric. Meaning, if you have two electrons of the same things, like say in one orbital you have two up, two plus half spin. Then they're going to cancel each other out. Since due to their anti-symmetric nature, they would cease to exist, and this cannot happen because they exist and it can't just vanish. So because of that, they have to be of opposite spins or not be of the same orbital. And here, but bosons don't have to follow this because they have an integer rule and their integer spin and their states allow for symmetric existence. So this is a meme made by the boson gang. So it was funny to just put that in. It's just mocking the fact that fermions can't exist in the same state. Okay, Saga, next slide, please. Okay, so now that we have, the two things that we need, basic understanding of the weak force and standard model, as well as Pauli exclusion principle, you can see, so there's something called the Chandrasekhar limit. So beyond 1.4 solar masses, this has been calculated by Chandrasekhar in the 1930s, I think. And so below 1.4 solar masses, the mechanism by which a white dwarf is stable can sustain the gravity. So what exactly is the mechanism? Sagar? Well, that's anticlimactic. Sagar, are you there? Okay, Nikhil, if you have a question, you can ask me, mate. I can answer by the time Sagar comes back. This is supposed to be like kind of a discussion, guys. It's fine. You can just feel free to unmute and ask. Can you hear me? Hello? Is it my fault or is Sagar's?
Yeah, we can hear you.
Yeah.
Okay.
Sagar, are you here? Yeah, Nikhil, you can maybe type your question if you don't want to unmute, or if anybody else has any comments about the session so far, you can feel free to.
Yeah, this is like a discussion, guys. It's fine. Just
Can you answer the previous question, Varun?
Oh, 1 second. Stars contain hydrogen, helium, so spectral lines received will be all of the elements together. Okay, that's a very good question. I'm afraid I do not know the answer. We need to wait for Sagar for that.
What about Serene's question?
What?
There is one more question. Maybe that's very specific to the equation. I don't know which equation.
Okay, yeah, even I don't know which equation.
Okay, that's it. You can take Nikhil's question.
I'm not entirely sure, but what exactly causes a supernova to release so much energy when all the fuel of the star has already been consumed? Okay, so when I mean by what I mean when I say fuel of a star is a fuel of a main sequence star, meaning the fuel being hydrogen. So there's something called binding energy. So this is basically the E equals mc squared, right? So this is the energy that is needed to separate either a neutron or a proton from the nucleus. Okay, so this is the binding energy of a nucleus. So to determine the stability of any particular atom or a nucleus, you need to look at something that is called binding energy per nucleon. So it's the total binding energy, but divided by the number of nucleons, which is either protons or neutrons, which is its atomic mass. So the higher the binding energy per nucleon, it means it would require more energy to break a bond, or rather to remove a proton from a nucleus. Uh, in other words, if something were to come to a state of higher binding energy, there would be a release of energy, because a higher binding energy implies a greater stability. So we know that whenever something comes to a more stable state, there's always more energy released. So an ion, or the iron atom nucleus, has the highest binding energy per nucleon. This is why I said iron was the most stable. So nuclear fuel won't exactly be done until yeah. Okay, I'll answer you, Vatsal, in 1 second. Uh, so when I mean by fuel, it won't be run out until iron has been reached. It's just that hydrogen to helium releases the most energy among the lighter elements. So now helium to carbon releases way more energy. Uh, so we see from helium to anything else like lithium or beryllium, as it's progressing, it doesn't release as much energy as hydrogen to helium. So a main sequence stars once that keeps burning hydrogen. So once it starts burning helium, it's going to contract because it doesn't release as much energy anymore. But in a supernova, when the masses, get, because there's more mass in the core where the nuclear reactions are happening, even the surface of the star gets into it. So now, because of this, it's going to start burning carbon and higher elements, which are more stable than helium. So this, like, higher stability, like a sudden jump causes, and the input of mass and the sudden jump in energy released causes there to be like a explosive reaction. Like it's going to be a vast difference in the energy release, because not only is it slightly better, but um, even if you're talking about per nucleon, there's going to be so much energy released. But the heavier any atom is, the more number of nucleons it will have. So you can think, say, if binding energy per nucleon would be 3 times as it was before, but an ion is 200 times heavier than hydrogen, so it's going to have 200 into 3, 600 times more energy released suddenly. So that causes an explosion of spurting out particles like all over. I hope that answers your question. Yeah. What's a planetary nebula contains star in the middle of it? Yes, it contains the core of the star in the middle of it. The outer layers disperse to form the planetary nebula, and the stellar remnant, or the core, or the actual star, if you will, is what remains at the center. I hope that answers that. Okay, so now where was I? Right, the mechanism by which a white dwarf is stable. So now that planetary nebula has been formed and the outer layers have been dispersed, there is still the core that is there. It does not burn anymore. There's no nuclear reactions happening anymore. So how does it remain stable? Won't the gravity just try to crush it? So now remember how we said fermions can't be in the same quantum state. So now as the gravity is crushing it, obviously you get more and more fermions, or in this case electrons, in the same state. Now the state where multiple fermions are being in the same energy level is called degenerate states. Okay. So now what you have a lot of degenerate electrons. So degenerate matter is a type of matter. It's not exactly another type of matter, but in a lot of quantum mechanics and astrophysics is used. Degenerate matter is basically matter which is free from any nuclear reactions. It's the purest form. It's akin to ideal gases in quantum mechanical systems. So degenerate electrons in this case, they would not like to be in the same state because of Pauli's exclusion principle. So they're going to try to avoid this as much as possible. So you're trying to compress something, but inherently universe does not allow, due to the wave function and antisymmetry, it does not allow multiple electrons to be in the same state. So it's gonna put an outward pressure that holds the gravity in place. Now this is very, very, very stable because this is a very fundamental reaction. It does not depend on any change of anything. It's just stable. But this also means this does not burn anymore. This does not have any more reactions to produce heat or light. So gradually the temperature and the luminosity of a white dwarf reduce. They keep falling. This is, when I mean very stable, I mean they, it's predicted to take 100 billion years for most white dwarfs to finish, not being able to hold this anymore. So it's most of the stars that we see are actually white dwarfs because they are intensely stable. But what if you have more gravity, one that can cross this limit being Chandrasekhar limit, where the electron degeneracy pressure, whether it be electron degeneracy pressure or neutron degeneracy pressure. And as everybody knows, its gravity is so much that even light can't escape. So now we'll have Sagar talk more about black holes and interesting quantum mechanical phenomena called Hawking radiation. Thank you.
Okay, guys. So actually, there is a question which asks: in sun there are hydrogen, helium, and many elements present. Then how the spectral science is calculated? So I'll try to answer it. I'll just stop the screen and I'll reshare. Okay. Okay. So can you see this? Can you see my screen, guys? Hello.
Yeah, we can see it.
So it says the sun spectral lines, isn't it?
Yeah.
Okay. So this is how the sun spectral lines are present. So here you can see that this is actually an absorption spectrum, but still it's no matter, it's not much difference. So here you can see that in an EM continuous spectrum, some lines are missing. So you can see that some lines in the red spectrum is missing and some in the blue spectrum and some lines are missing red. So those missing lines correspond to the they actually correspond to the actual elements present in sun. See, for example, you can see hydrogen has so many lines and iron has a bit more. But you can see this actually what they do is they find out the percentage of the matching. See, they got one spectral lines. They see how much percentage is it matching with each of the element. So they match with hydrogen. So they say that 91% is matching with hydrogen. And then they find out with some other element. And they say that some percentage is matching with that element. So these are we can calculate the actual percentage of atoms present in an luminous object. But actually, why didn't I include? Because this actually contains so many equations that we can't actually understand right now in this time constraint. So that's why I didn't include. But this is how they do. They actually find out the percentage of spectral lines which is matching with each element, and they find out. Okay, so this is how they do. So I'll be continuing with my next topic. I have to stop sharing and I'll reshare. Okay, so can you see the reshared again the slide which says degeneracy pressure and Chandrasekhar limit?
Yes, Sagar. Okay.
Can anybody tell?
Yeah, bro, we can see it. Can you hear us?
Okay. Yeah. So now, can anybody guess what equation is this? Can I get some response in chat box? What equation is this?
Einstein field equations.
Exactly. So this is Einstein's field equation, which is present. So what does this equation tells is it relates the two important factors, that is stress and energy of a matter to the gravitational field. So T mu nu is the stress energy tensor, which is actually caused by the matter, that is the mass present in the space time, and G mu nu is the gravitational field which is generated by that mass, and capital G mu nu is the Einstein tensor. So we can't go detail to this field equation because of the time constraint which I said earlier. So this equation, what it gives is it relates matter with gravitational field. So it actually says that how matter causes the curvature in space-time. So here a small depiction how we can understand it. So here we see that Earth, because of its huge mass, it is curving the space-time and causing a dip. It's actually not a dip actually. It's like the grids of the space lines, they actually bend and such that the movement of this moon which is revolving around Earth it's actually changed. So this is the equation. This is what the equation tells. So this given by Einstein's general relativity actually. So um, but after Einstein gave his general relativity, there was this scientist called as Schwarzschild. So Schwarzschild, what he said is, he said that let it be an any celestial object M, if it is compressed such that its radius became less than some value called Rs. That is Rs is equals to 2gm by c square. So let there be any object, let any object be whose mass is capital M, and if that object is actually compressed so that its radius become less than this value, this is called as the Schwarzschild radius. So if the radius of that object becomes less than this value, it actually manifests the space-time so much that there's some new object can be created. So actually it's not new object created, but it's like the density becoming high and it causing a new change in the space-time. So something will happen. This is what Schwarzschild told actually. So that is nothing but black hole. So black hole, you mean it doesn't mean it's black. It means that it's not leaving any radiation out. Now you can see in my next slide that some important parts of black hole you can see. So you can see accretion disk. So accretion disk is the disk caused due to the gaseous particles, heated atoms which are surrounding black hole. And then there is event horizon, which is like the boundary between outer space and the black hole. It's just the boundary. It's like the boundary between our outer space and black hole. And inside event horizon, there is something called as singularity. So singularity at the center of black hole has infinite density, and all matter or light, anything what black hole absorbs go there. So that is called as singularity. So the singularity is like it's having zero volume. It has infinite mass and zero volume. So its density will be still higher. So this is what singularity says. Singularity means. So we can understand that in singularity, space-time is warped so much that even light can't escape. So in this image, you can actually see that if there is some other object, consider any star, it bends the space-time a little bit. And light, what does it? If light is passing through near to that object, due to the curvature of space-time, light which follows the geometry of space-time bends, and then it is deviated. So this is what happens if there is normal star present. But what happens if actually black hole present? If black hole is present, what happens is the light, as soon as it crosses the event horizon, you can see event horizon that's present here. As soon as the light crosses this, light cannot deviate. It just goes into singularity. Light cannot escape singularity. So this is what happens in black hole. So now one thing you have to notice that since black hole can't escape, since light can't escape black hole, then there will be no radiation emitting from black hole, right? See, now we know that any object, if it is having some temperature, as we saw in blackbody radiation, then it has to emit light. But here we can see that black hole is not at all emitting any light, because since it's having infinite mass, it's not allowing any light to escape. Then the temperature of black hole actually has to be zero, right? According to blackbody radiation, any object is, if it is emitting some radiation, its temperature will be higher. Like higher the temperature, longer the frequency, higher the frequency, and lesser the wavelength. Now here, since it's not at all emitting any radiation, its temperature has to be zero. This is what we understand. Okay, so here we can see that as temperature becomes zero, the spectral energy density becomes zero, according to the equation. But is this happening really in black hole? So non-zero temperature of black hole actually is present and this was given by the famous scientist Stephen Hawking. So in 1974, Stephen Hawking showed that temperature of black hole will actually be non-zero. Rather, it will be a value of h bar c cube by 8 pi g kbm, where h bar is the reduced Planck's constant, c cube is the cube of the speed of light, g is the gravitational constant, kb is the Boltzmann constant, and m is the mass of black hole. So Stephen Hawking, what he said is the temperature of black hole will be this value, and if we calculate this, it's actually 6 into 10 power minus 8 Kelvin. That is 60 nano Kelvin divided by the mass in solar masses. So a black hole of 1 solar mass will have a temperature of 60 nanokelvins. That is actually not equal to 0, right? Then if temperature of black hole is not 0, then it has to emit some radiation according to Planck's law. Then what is this radiation called? So that is called as Hawking's radiation. And actually here is a graph showing the relation between temperature and mass. So since by this equation we can get to know that temperature is inversely proportional to mass. So if we plot this, this will be the graph. So as temperature increases, mass decreases, but if mass increases, temperature decreases. So this is how we can see the relation between mass and temperature. So if temperature is not 0, then it has to emit radiation, as I said. So that radiation is called as Hawking radiation. So Hawking radiation actually can be calculated by some equations, which I'll tell in later stage in the presentation. Now here is a table showing the relation between mass, frequency of Hawking radiation, and wavelength of Hawking radiation. So here they say that a black hole of 5 solar masses has this frequency, and the Hawking radiation has this wavelength. So and actually we can see that the wavelength of Hawking radiation is very large. It's like some 37 kilometers. So the wavelength is like 37 kilometers, 44 kilometers. So it's okay, sorry, 445 kilometers. It's such high wavelength, and frequency is actually very small, like 800 hertz. So very small frequency. So but still the frequency is very small and wavelength is very large. It's emitting some radiation. That radiation is called as Hawking radiation. Now, how did Stephen Hawking predict this Hawking radiation? We'll see that. And there is also he predicted one astonishing concept called as black hole evaporation. So what he said that black holes evaporate, like black hole is present, after some years they just evaporate. This is what Stephen Hawking said. He also gave the formula that T is equals to 5120 pi g square m cube by h bar c power 4. So he related mass of black hole with the evaporation time. So we can see that the mass of black hole, if it is 1 solar mass, it evaporates in 2.13 into 10 power 67 years. So even though the time is very longer, actually it's 4 times longer than not 4 times. It's actually like 8 times longer than the age of universe, but still he showed that black holes evaporate. What if the mass is very small, like 10 power minus 9 solar mass, a very small black hole? Still it evaporates, right? It actually evaporates a little more quicker if the mass is very small. So he showed that black holes evaporate. Now how did Stephen Hawking predict this Hawking radiation? How did he find that equation which shows black holes have non-zero temperature, and why black holes evaporate? So this is where quantum mechanics come into action. Now, quantum mechanical approach to Hawking radiation. Okay, now we all know that space is made of vacuum. Is it truly vacuum? That means the space is completely devoid of matter and energy of any kind.
You're muted, sir.
Guys, I'm confirming again. Can you hear me again, guys?
No, we can hear.
Yeah, we can.
Okay. Sorry, my internet is really bad, so I have to confirm. Okay. So what I was telling is, if we say that energy is is not present in a region of space, then we're actually violating an important principle called as Heisenberg's uncertainty principle. So Heisenberg's uncertainty principle says that delta E times delta T is greater than h bar by tau. It means the error in energy times the error in time interval is should be actually greater than this non-zero quantity, that is h bar by tau. So if we are telling that 100% energy is not present in vacuum, then delta E is 0 because we are 100% sure that energy is not present. So we are uncertainty is 0. That implies that temperature, that is the error in time is infinity, which is actually meaningless. So then there has to be some energy present, right, in vacuum also. So that is where quantum field theory comes. So in quantum field theory, universe is considered to be made of quantum foam, where all the quantum activities happen. So what is this quantum foam? Consider you're present in a universe where actually instead of seconds, see, like if you count 1, 2, 3, you say that 1 second passed or 2 seconds passed. But instead, if it is nanoseconds what it passes, you're in a nano world, and the space is not meters, it's like nanometers or picometers. In such a space, that is, if we zoom our world totally into picometer level, then what we see is this. This is called as quantum foam. That is where you can see that from the space, some object is coming out, and some entanglement, like here, something is happening, and here some activity is happening, some quantum tunneling, something is happening. So these activities actually occur in quantum foam. That is the universe where we zoom it totally into nanometer or picometer scale, and time is like nanoseconds. In such a world, we see this quantum foam. So according to this quantum foam, what it tells us is, even in pure vacuum where there is nothing, there are some particles which can arise, annihilate, and disappear. So here you can see a small GF video where it says, where it shows some particles emerging out and suddenly disappearing. You can see that, right? So this is actually happening in vacuum. So what is this? Now we know that according to Heisenberg's uncertainty principle, delta E times delta T is greater than or equal to h cross by tau. So if the particles arise at a very short time, such that delta T is very zero, that is their lifespan is very zero, they can have very high energy, right? Delta E can be very great. That is, delta E can be very high value. That means if these particles what arise suddenly from quantum foam, and if they are having very short lifespan, that is delta T is very small, they can have any amount of energy in them. So this is what Heisenberg's uncertainty principle tells us. So as long as their lifespan is very small, these particles which arise just like from from vacuum, they can do anything. Like they can come, do any activity and go back, such that their lifespan is very small. So this is what quantum field theory tells us. So if such particles arise by borrowing energy from universe, they have to repay the energy back into universe within the time delta T. But quantum mechanics also tells us that if particles arise, then they can't arise simply. They have to arise only in pairs. That is, one particle will be a normal matter, but another particle has to be antiparticle. So this is what quantum mechanics tells us. And actually what happens is, these particle pairs arise, they live in the short duration delta T, and they annihilate back and go back to universe. So this is what quantum mechanics tells us. So far so good. But what happens actually if a black hole is present. Actually, here is the description how particles arise. So here you can see a blue is a normal particle and red is the antiparticle. They just arise, they live for a short time, they annihilate back and go back to universe. So this is a vacuum is present actually. So according to quantum field theory, this is a vacuum is. So particles arise, live for some time, annihilate back. So this is okay. But what happens if black hole is present? So if consider a black hole is present and we can see the event horizon, and there are two particles which just arise. Let the particles be any particles, we just assume it electron and positron. So electron and positron are right very close to event horizon. So these particles are very small, right? So they can even quantum rules can apply on them because they're very small and their mass is very low. We can apply quantum mechanics. So they actually exist in wave function, isn't it? So the particles, electrons and positrons, since they are very small, we can describe their position in wave functions. So consider the red particle. So the red particle was actually positron and blue particle is electron. So consider, so positron is here, like in red sphere, and electron is in the blue sphere. This is the wave function of the particles. Now, since the wave function can be spread out, that is, if we didn't violate probability conservation, that is, the probability actually has to be 1 in this region. So if we conserve the probability, they can spread out in space, right? Such that the sum of probability is still 1. So if they spread out in space like that, there is an equal chance that one of the particle can go inside. There's a wave function of one of the particle can go inside the event horizon. There is a pretty good chance that the wave function will cross the event horizon, and due to wave function crossing the event horizon, there can be a phenomenon called as quantum tunneling happening, where one particle suddenly quantum tunnels inside the event horizon, leaving the other particle just outside. So now we know that if any particle, if it goes inside the event horizon, it can never come back. That is the property of black hole. Since the black hole makes this space-time very warm, the blue particle, it just goes inside black hole and go to singularity. But what happens to this red particle? The red particle is alone. It's actually waiting for blue particle to annihilate back and give back the energy to the universe. Since they're virtual particle, they borrowed energy, they came to existence in pairs, but one of the particles just goes into black hole. Then what happened to this blue particle? So we can't violate this energy, right? Energy has to be given to universe back. So what happens is that energy will be given by black hole. So that energy given by black hole will actually be in the form of Hawking radiation. So this is why black holes emit radiation, which is called as Hawking radiation, just to repay back the energy borrowed by these particles. So this is why black holes actually transforms its mass, some of its mass, to energy and give back in the form of Hawking radiation. So thus, if these virtual particles get trapped in black hole, then to compensate their energy, black hole radiates Hawking radiation into the universe. So this radiation is responsible for non-zero temperature of black holes, isn't it? So we got the answer that why Hawking radiation is actually produced. That is because of these virtual particles which are present, which suddenly is sucked by black hole, or when they quantum tunnel into black hole through event horizon, and then one of the particle is remaining outside. Thus, just to compensate their energy, black hole transforms some of its mass into Hawking radiation and emits out. So this is how Hawking radiation is produced according to quantum mechanics. So this is how quantum mechanics is important. Now my friend Kushal is going to explain some more concepts of application of quantum mechanics in
Sagar, do you think you can answer the
astronomy.
questions
So
for us?
Kushal, you can continue.
Bro, there's some questions in the chat. Can we answer that first?
So Kushal.
Yeah.
Sagar, there's
So
actually some
David,
questions in the chat. Do you want to answer that first?
Okay, then I'll answer it.
yeah, okay.
Okay. From where the question started? Can somebody read the questions? Sitara, can you do it?
Sagar, can you answer this question, like why is space-time always depicted as flat when it's actually 3D?
Okay. So now we know that we are in our undergraduate level, we are actually working out with 3D analytical geometry, isn't it? Like we know vectors, X, Y, Z components, and so that's how we are working. Now, is that easy to work 3D? There are so many equations, so many formulas which we apply in 3D geometry. Now, if 3D geometry itself is so much hard to work on, and it's very tough to depict 3D in a 2D paper, then will it be easy to depict a 4-dimensional space-time in our paper? It's very, very tough, right? You might have all seen the image of a tesseract in computer screens, which will be a 2D, which it's actually a 2D depiction of tesseract, right? Nobody has seen tesseract in 3D unless they create a 3D model and they show tesseract. Until then, we can't imagine 3D object of tesseract. Now, can we imagine 4D object? Now, it's actually out of our imagination. We can work out 4 dimensions in our paper, but it's very tough to imagine 4D object because we are 3-dimensional beings. So that is why what we do is we take the easy approach of a flat space-time. Actually, space-time is actually 4 dimensions, 3 dimensions of space and 1 dimension of time. So it's a 4-dimensional object. Since we can't depict 4-dimensional object in our 2D screen, we just show it in flat 2-dimensional space as a space-time fabric. It's actually 3-dimension. You can show it in 3-dimension depiction, but it's very tough to show in our 2D screen. That's why many scientists or researchers show it in a flat uh, as a flat disk. Okay, next question.
And the next question is from Serene. Why light cannot escape black holes since it has no mass?
Okay. Now one thing you have to understand is gravity is not caused by mass. Actually, it's caused due to energy and stress it's producing, isn't it? As we know in general relativity, energy is what being affected by gravity. Energy creates curvature, and curvature affects energy. Now we know matter as energy, so we say matter affects space-time, space-time affects matter. But actually, it is the energy inside this matter which is causing the change. Now we know that light has photons. Photons has energy. Now that is why they are being affected. And moreover, photons are not affected due to their mass, rather the path they follow. Now photons always follow space-time, right? In flat space-time, they just go in straight line. But if there is a curved space-time, like if there is a large mass present, then what happens is the space-time itself curves, and the light which follows the space-time has to bend. There is something called as geodesic trajectory what the light follows. The curve what light follows in a curved space-time is called as geodesic, and that's actually due to the curvature of space-time, and light which is following the curvature will bend. It's not due to the mass actually. So next.
Also, another cool thing, like because of that, it's light does follow rectilinear propagation. It does move in a straight line. It's just that the definition of a straight line itself changes because space-time changes.
Exactly. So actually, in curved space-time, the straight line is not the quickest movement for light actually. So we can say that the shortest distance between a paper, in a paper, if you want to do the shortest distance, we just draw the straight line. But actually that is not true in the curved spacetime. In curved spacetime, the geodesic trajectory is the shortest distance instead of a straight line. Okay, next.
Next question is from AK. So black hole is really a hole or is it a sphere?
Black hole, actually we can, what we see is it's actually like a sphere actually, right? There is a singularity. Nobody knows what singularity is, what is the shape of singularity, but the event horizon and the accretion disk, what is present around black hole is actually like which follows as if the black hole is sphere. So I think black hole is a sphere, or it can be a point mass actually. Then next.
Next question is from Abhishek. Can a black hole swallow another black hole?
Yeah, they can. You know this binary revolving systems, right? Where black holes spin and they go in spiral mechanism and finally they merge and cause a bigger black hole. So that's how a larger black hole can mix or merge with smaller black hole. It's like black hole sucking another black hole. It can be like a large mass black hole sucking a small mass black hole. That can happen, yeah. Next.
How do we calculate the mass of a black hole?
Okay, so mass of black hole is actually calculated through the calculations of by seeing the Hawking radiation actually. So now we know that black holes emit Hawking radiation, and now what the scientists do is they find out the deviation of the light takes. Now we know that mass curves space-time, and space because of the curved space-time, light actually bends.
I
Now
think you mean
what scientists do is
gravitational
they
lensing,
find out the amount of bend the light does. Like if the mass is very high, it bends less. I'm not telling the bend of light which goes inside event horizon. I'm telling the bend of light which the light will bend just outside the event horizon, not inside the event horizon. Okay, so what happens is they see the amount of curvature or bending of light which light travels just outside the event horizon, and find out if the mass is very high, light bends so much. So light is bending this much, so mass has to be this quantity. So that is how they calculate mass of black holes actually. Then next question.
Isn't it due to the trajectory of the nearby stars? Because Hawking radiation has not been detected yet.
I'm not telling about Hawking radiation. The light which actually the light which crosses the black hole, the light which doesn't, okay, I'm not telling the light which crosses event horizon, the amount of gravitational lensing, that is what determines the mass of
no, you
black hole.
don't know exactly how much.
If you know what is gravitational lensing, then you come to know the amount of light bend, and then you can find out the mass. Or Aditya, I think you can give a good explanation now.
Like as far as I know, at least at the beginning, it was due to most black holes. You can, especially at the center of the galaxy, you can see the trajectory of the nearby stars that are orbiting it. So you can calculate the mass of a star, and you can by the orbit of the star around the black hole, you can calculate the mass of the black hole.
Yeah. So actually, that way is possible only if black hole is present in the center of galaxy. But if there is a lone black hole which is alone, like there is no nearby stars, then gravitational lensing is the good method. So next question.
How can something emerge out of nothing? Doesn't it violate conservation of energy?
Actually, conservation of energy is still being followed. See, I'm not telling energy is created and remains as such. Energy is created and repaid back. Now, we can't tell that 100% that energy is being created and energy is being given back, because that also violates Heisenberg's uncertainty principle. So because of this Heisenberg's uncertainty principle, we can tell that energy emerges out from vacuum within the delta t time, that is the delta t, which is the uncertainty in time. Within that time period, that energy can go back. So then energy is actually not, conservation of energy is not violated. Rather, it's having some uncertainty in that conservation of energy. That is, energy is produced within the short time delta t, it's given back, isn't it? But if that is violated because the one of the particle goes inside black hole, then that is a violation of is the violation of energy, because energy is not repaid back. That is why black hole emits that energy. That is, the black hole repays that energy to universe. So next question.
So if smaller mass black holes evaporate at a faster rate, does that mean there is a possibility of infinite black holes around us but too hard to detect?
Yeah. So this actually brings us the concept of primordial black holes. So actually, what scientists say is there are very small black holes which are like very small, like 100 kg black hole or 1 kg black hole, which is evaporating fast, and it also have some anomalies in gravitational waves and many other things. So actually, it brings us to the concept of primordial black holes. So actually, I didn't prepare much about that. So I'm giving a way to for future studies. Next.
What is the order of energy produced by quantum foam? Can it be used for propulsion?
Actually, energy what it is given by quantum foam has to be repaid back to the universe, right? The energy which is got, actually the energy created by this quantum foam, it will be given, and within time delta t it has to repay. I don't think we can use that energy, or rather what we can do is we can take that energy and repay back in some other form. Like if you have some sun, some star, we can take energy from quantum foam, but repay back that energy through that sun, and I think we can use that energy. But unless we conserve this energy, that is within delta time t, delta time, we have to repay back energy. So unless we do that, I think we can't use quantum foam's energy. Next.
If one particle gets sucked into the black hole, how can its counterpart escape when black hole gravity is incapable?
See, any particle cannot escape if they go inside event horizon. I actually showed in the space-time diagram that if any particle, light or any particle, if it crosses event horizon, then it cannot escape black hole. But if it doesn't cross event horizon, there is this part called as inner stable orbit around black hole. That orbit, what it does is, as long as the particle doesn't cross event horizon, the particles can escape black hole. Now moreover, since the mass of these particles are very small, actually they can be cancelled, because mass of black hole is very high and mass of black hole is mass of particle is very small. So still black hole has so much pull, it cannot affect these very small particles. Now we also don't know how gravity acts in quantum particles, right? Because gravity, general relativity is only for higher classical objects, not for quantum objects. So still we don't know the accurate depiction how gravity acts for this quantum particles. Next.
What decides the time interval in which particle and antiparticle has to annihilate back?
That is given. That's actually governed by Heisenberg's uncertainty principle. Now, see, if some particle arised, consider a proton and antiproton is arised. Okay. Now, the what energy they take, that energy will be equal to E is equal to mc square, right? Now, since proton and antiproton have same mass, the energy they borrowed from the universe will be 2mc square. Now we know the delta E value, that is 2mc square. Now we just apply the Heisenberg's uncertainty principle. Delta T is equals to h bar by 2 into 2m square, 2mc square. So that is how we can calculate the delta T value. That is h bar by 2 into the energy what they have taken. So that within that time gap, they have to give back that energy. So next.
The time in which virtual particles arise and go back, is it tending to being instantaneous?
That can see instantaneous. We mean zero temperature, zero time, right? Instantaneous means as soon as this happens, this will happen. That is actually 0 seconds. But actually, the time period of the lifetime of these particles is not zero. They have some non-zero temperature. So that is why in quantum scale, that is not zero, that is not instantaneous. But for us being classical objects, we being classical objects, for us it is very, very quick, like 10 power minus 12 seconds. It's very, very quick for us. But in quantum realm, that is not quick. There is some time lag between their birth and death. So it is not instantaneous in quantum realm, but it is instantaneous for classical objects like us. So next.
If matter and antimatter pairs are produced, then will there be Hawking radiation which may consist of antimatter rather than matter?
Can you read the question again?
If matter and antimatter pairs are produced, then will there be Hawking radiation which may consist of antimatter rather than matter?
Yeah, there can be any particle going inside black hole, right? See, if matter goes inside black hole, antimatter is ejected as Hawking radiation. If antimatter goes inside black hole, matter is ejected as Hawking radiation. That's all. Next.
Sir, hello.
Yeah, tell.
Yes, sir. Why it is happening like this? Means a particle is going. Means this particle get into a black hole, then antiparticle will emitted as a Hawking radiation. Why it is happening?
I was not able to hear you. Can you hear again? Can you tell again?
Hello. Yes, sir.
Yeah,
My
tell.
question is, hello. Yeah. If particle is going into the black hole, then why particle is emitted as a Hawking radiation? Why it is happening so?
Can you type the question in chat box because I'm not able to hear it clearly.
Sagar is asking if
Yes.
particle is goes into the event horizon, why is antimatter like emitted as Hawking radiation?
Guys, your voice is cracking a lot. Is
Hello.
my voice
So I'm
cracking?
typing in.
Okay,
Yeah.
okay.
No, no.
I think I can answer that. If Sagar can't hear it. Okay, so irrespective of whether matter or antiparticle or antimatter, falls into a black hole, it's going to be converted to energy. Like there is nothing distinguishing between matter and antimatter at that scale. Like it's all going to come crashing down to one point where it's just pure energy. And this energy, which is released later, has to be in the form of a particle antiparticle pair due to various reasons I've explained in the chat box, mainly conservation laws. So once it becomes just pure energy, it is expelled indiscriminately. The another thing is this also leads to another problem. It's called the information loss paradox. Basically, quantum information is being lost. So you can't say whether normal matter or antimatter has fallen into a black hole. Once something falls into a black hole, it becomes a part of it, nothing more, nothing less. There really isn't much distinguishing factor. And so whenever energy is released, namely in the name of Hawking radiation, it's going to be in the form of pair production, irrespective of what had fallen into it previously.
Yeah, actually,
I hope that answers
even
your case.
quantum information paradox come under quantum mechanics, where it tells that if something goes into black hole, then the radiation emitted will always be the same, right? Consider two black holes which are having equal masses, like two solar masses black hole. There are two black holes, two solar masses black hole which are two in number. In one black hole, and a satellite fell, and in another black hole, some star fell. Okay. Now the Hawking radiation, what is given by the black hole, will always be the same, right? Hawking radiation, as we calculate, it doesn't include the information of the falling object. Rather than it just includes the temperature and the mass of black hole. It doesn't include any information about the falling object. So that is where we lose the information that is going inside black hole. So any information that goes inside black hole is always lost. That means we can't get back the information. Now Hawking radiation is not giving any information as such. Rather than it just gives the information about mass and temperature. So this is actually a small concept of information paradox. The next question.
Sagar, I think no more questions.
Okay then. So Kushal, you can continue.
Yeah. Thank you, Sagar, for your informative session. So the next topic is going to be nuclear fusion in star cores. Sagar, next slide. So stars are made mostly of hydrogen and helium, which are packed so densely that in star center the pressure is great enough to initiate nuclear fusion reaction. Nuclear fusion reaction, the two nuclei of atoms combine to create a new atom. Most commonly in this core of a star, two hydrogen atoms fuse to become a helium atom. Sagar, are you there? Previous slide. Most commonly in this core of a star, two hydrogen atoms fuse to become a helium atom. Although nuclear fusion reactions require a lot of energy to get started. Once they get going, they produce enormous amount of energy. The inside of a star is hot and dense, and all of these hydrogen atoms keep bumping together and they fuse to form helium. The sun's been doing this for nearly 5 billion years. Eventually, the hydrogen in the center of the star runs low, and we have mostly got a lot of helium jostling together instead. Saga, the next slide. When hydrogen fusion stops, the star is no longer in equilibrium and the core shrinks down. In the sun, this is where things will end once the helium runs low. Saga, next slide. But this makes things even hotter, so the star can start to fuse helium into carbon. Next slide. But if a star is much bigger than the sun, the core will shrink again and it will get even hotter at the center. Now the star can fuse together a carbon and a helium atom, creating oxygen. Next slide. You can imagine what happens when carbon runs low and fusion stops once more. The core shrinks, things get hotter, a new fusion can begin again. Helium and oxygen start to fuse into neon. Next slide. Depending on the size of the star, this process can continue through the periodic table up to the point where iron is formed. But to fuse iron, you need to input energy. With energy going into fusion, instead of coming out of it, the star can never be in equilibrium. And again, its days are numbered. Next slide. Stars are in constant struggle between gravity and trying to collapse them. Stars are in constant struggle between gravity trying to collapse them and their internal heat trying to inflate them. For most of a star's life, these two forces are at an uneasy truce. Next slide. For a star like the sun, the balance tips in its twilight years. For a brief, glorious moment, it expands, but then blows away its outer layers, leaving behind the gravitationally compressed core. It goes out with a whimper. Well, a whimper from a 2 octillion ton barely constrained nuclear-powered fireball. But more massive stars aren't quite as resigned to their fate. When they go out with a big, very big bang. Next slide. In the core of a star, pressure and temperature are high enough that atomic nuclei can get squeezed together and fuse. This releases energy and creates heavier elements. Hydrogen fusion makes helium, helium fusion makes carbon, and each heavier element in general takes higher temperatures and pressure to fuse. Lower mass stars like the sun stops at carbon. Once that builds up in the core, the star's fate is sealed. But if the star is more than 8 times the sun's mass, it can create temperatures in its core in excess of 500 million degrees Celsius, and the carbon will fuse. There are actually a lot of steps in this process, but in the end you get carbon fusing into neon, magnesium, and some sodium. What happens next turns back to what we found in the sun's core as it ages. Fuse an element, create a heavier one, then that heavier one builds up until the core contracts and heats up enough to start fusing it. So carbon fusion makes neon, magnesium, and sodium, and those accumulate. The core heats up, and when it reaches about 1 billion degrees, neon will fuse. Neon fusion creates more magnesium, as well as some oxygen. These build up in the core. It shrinks, heats up to 1.5 degrees Celsius, and then oxygen fuses, creating silicon. Then that builds up until the temperature hits up about 2 to 3 million degrees, whereupon silicon can fuse. Among a pile of other elements, silicon fusion creates iron, and that's trouble, big, big trouble. Once silicon fusion starts, the star is a ticking time bomb. Next slide. But before we light that fuse, let's take a step back and let's see that what's happening to the outer layers of the star. What do we see if we are outside looking back at it? Because the star was born massive, it spent its hydrogen fusing days as a blue main sequence star. Stars like this are extremely luminous and can be seen from tremendous distances. Like the sun, though a massive star, changes when hydrogen fusion stops and its core contracts, and then helium fusion begins. It swells up, just as the sun will. But instead of becoming a red giant, it generates so much energy, it becomes a red supergiant. Next slide. These are incredibly huge stars, some over 1 billion kilometers across, and they are luminous. For example, Betelgeuse in Orion is a red supergiant and one of the brightest stars in the sky, despite being over 600 light years away. From the distance, you'd need a decent telescope to see the sun at all. Next slide, Sagar. And that's nothing compared to VY Canis Majoris, the largest known star, which is a staggering 2 billion kilometers across. We even have a special term for it, a hypergiant. Next slide. You might think massive stars would last longer because they have more fuel than lower mass stars, but the cores of these monsters are far hotter, and they fuse elements higher at higher rates, running out of fuel more quickly. A star like the sun can happily fuse hydrogen into helium for over 10 billion years, but a star twice as massive as the sun runs out of hydrogen in just 2 billion years. A star with 8 times the sun's mass runs out in only 100 million years or so. Next slide, Sagar. And each step in the fusion process happens faster than the one before it. In an extreme case, like for a star 20 times the mass of the sun, it will fuse helium for about 1 million years, carbon for about 1,000, and neon fusion will use up all its fuel in a single year. Oxygen lasts for only a few months. Silicon fuses at higher rates than oxygen. The star will go through its entire supply in get this a day. After what silicon, it just takes a day for the star. Yes, just one day. The vast majority of a star's life is spent fusing hydrogen. The rest happens in a metaphorically blink of the eye. Next slide. Silicon fuses into a bunch of different elements, including iron. The inert iron builds up in the core, just like all the elements did before. And just like before, the iron core shrinks and heats up. But there's a huge difference here. In all the previous fusion stages, as we saw before, the energy transforms into heat, and that helps support the soul-crushing amount of the stellar mass above the core. But iron is different. When it fuses, it actually sucks up the energy instead of creating it. Instead of providing energy for the star, it removes it. This accelerates the shrinking, compressing the core and heating up even more. Even worse, at these temperatures and pressure, the iron nuclei suck up electrons that are whizzing around, which are also helping support the core. Means of support for the star are removed in an instant. Silicon fusing into iron is happening so fast, this literally takes a fraction of a second once it gets started. The core gets its leg kicked out from under it. It doesn't shrink, it collapses. The gravity of the core is so mind-bogglingly strong that the outer parts crash down on the inner part at a significant friction of speed of light. This slams down on the central core, collapsing from several hundred kilometers across down to a couple of dozen kilometers across in just a few thousandths of a second. The star is doomed. Next slide. Now at this point, one of two things can happen. If the star is less than about 20 times the sun's mass, the core collapses. The core collapse stops, and when it's still 20 or so kilometers wide, it forms what's called a neutron star. If the star is more massive than you think, if the star is more massive than this, which is 20 times the mass of the sun, then the collapse cannot be stopped by any force in the universe. The core collapses all the way down to a point the gravity becomes so intense that not even light can escape. A black hole is born, as Aditya explained about all this. But for now, what happens when the core collapses and suddenly stops? The core of a star, whether it's a neutron star or a black hole star, is now extremely small, with terrifyingly strong gravity. It pulls on the star's matter above it. This stuff comes crashing down at a fantastic speed and gets hugely compressed, heating up, uh, furiously heating up. Next slide. While this stuff is falling in, a monster shock wave created by the collapse of the core moves outwards and slams into the incoming material. The explosive energy is so insane it slows the material sustainability. Next slide. The second event is the complicated quantum physics brewing in the core generates vast number of subatomic particles like neutrinos. The total neutrinos carried by the light, next slide, sir. The total energy carried by the little neutrinos is almost beyond reason. In a fraction of a second, they carry away 100 times as much as energy as the sun will produce over its entire lifetime. That's an incredible amount of energy. They hate to interact with normal matter. One single neutrino could pass through trillions of kilometers of lead without even noticing. But so many are created in the core collapse, and the material barreling down on the core so dense that a huge number of them are observed. This vast wave of neutrinos slams into the oncoming material like a bullet train hitting a slice of warm butter. The material stops its infall, reverses the course, and blasts outward. The star explodes. It explodes. Next slide. This is called as supernova, as it was again explained by Aditya, and it is one of the most violent and terrifying events the universe can offer. An entire star tears itself to shreds, and the expanding gas blasts outward at 10% the speed of light. The energy released is so huge they can be seen literally halfway across the universe. They outshine all the stars in the rest of the galaxy combined. The expanding material called the supernova remnant forms fantastic shapes. The most famous is the Crab Nebula, right on the left-hand side on the top. From a star we saw blow up in the year 1054. Betelgeuse will certainly explode someday, but it's too far away to hurt us. Supernovae are how the majority of heavy elements in the universe are created and scattered. The calcium in our bones, the iron in our blood, and the phosphorus in our DNA, all created in the heart of the titanic depth of a star that blew up more than 5 billion years ago. Next slide. Now, ever wondered why the sun keeps shining? Well, the answer for that comes with the next concept. Next slide, Sagar. The next topic is going to be quantum tunneling of photons in stars. Next slide. Next time you look up at the big nuclear fusion plant in the sky, which is the sun, know this: the sun actually is too cold to make the amount of energy it makes. Well, it would be too cold if we only believed the older classical physics of the 19th century. If the sun actually generated energy through heat alone, like a giant fireball, it actually would have burnt out millions of years ago. So if the big ball of fire and gas up there doesn't provide energy through heat alone, next slide, how does it do? Like other stars, the sun shines through the energy generated in the middle in its core. It generates incredible energy and heat through what's called nuclear fusion, as we saw earlier. This is when atoms combine together, form different atoms, and often release subatomic particles like neutrons, protons, or gamma rays while doing so. We are sure you have studied that at school, but these subatomic particles are the bits that make up all the atoms. The temperature in the core of the sun is about 15 million Kelvin. Next slide, Sagar. The pressure in the sun's core is 250 billion times greater than our atmospheric pressure. And even at the absurdly high temperature and pressure, it isn't even close. Next slide. See, the sun is made up of 90% of hydrogen, which is its source of energy. Every hydrogen atom has a proton. All protons carry a positive charge, and so they repel each other. The closer they get to each other, the more they repel, a bit like a strong magnet. Scientists call this Coulomb repulsion force, a force so strong that at the temperature of the sun's core, no hydrogen protons should even fuse together. So what would you need to get past this force? A lot of heat, not some lighting of fire. It's like 15 million Kelvin, more like not even 15 million Kelvin of the sun's core. It's like 10 billion Kelvin, which we require to make both the hydrogen protons to fuse together. But the sun's temperature is not even close to that number. So what's really happening here? Next slide. This is where we have to bring in the strange world of quantum mechanics. At this fundamental level, a level so tiny that we are talking about the insides of the individual atoms, where subatomic particles like electrons and protons also behave like waves. Next slide. But you can imagine each proton is also a wave, and the waves of two protons can sometimes overlap a bit. There exists a small probability that two protons overlapping uh, can overcome the repulsive force through the scientists with called the quantum tunneling. This will mean that a proton will appear next to the other proton so they can fuse together. For tunneling to happen, you don't need 10 billion Kelvin like a normal fusing. Actually, 15 million Kelvin will do. Tunneling can happen at this low temperature, but extremely rarely. A single proton needs to wait billions of years before it can fuse with another to make helium this way. But because the sun is massive and it has so many protons, statistically fusion happens even with this super low probability, just at a very slow rate. So what really happens once the protons tunnel through each other? Next slide, Sagar. When protons of the hydrogen atom fuse together, they make helium. This also releases energy as gamma photons. This process is called as proton-proton reaction chain. All protons are particles of light, but within photons, gamma photons are much more powerful and we cannot see them. The gamma photons are created in this proton-proton chain are the source of the energy of most of the stars in the universe. This gamma energy is mostly created in the core and then starts a long journey to the surface of the sun. When I say long, I mean more than 100,000 years. A few 100,000 years for one gamma photon to reach the surface of the sun, going through all the different layers of the sun. This means by the time they reach the surface, their energy is reduced and they mostly emerge as photons that make up visible light. It then takes a little more than 8 minutes to reach the sun, to reach us on Earth. That means the light you feel on your face when you're outside right now, maybe that was made in the sun's core before the first humans were coming out of Earth. There's another critical process that makes fusion even slower, which is the weak force, which was explained by Sagar again. It's a fundamental force and it is essential in making helium atoms by turning protons into neutrons in this reaction. It's also very, very slow. It's the low probability of quantum tunneling and the super slow rate of the weak force process, which makes the sun burn bright for a long, long time. Next slide, Sagar. So till now, it's just amazing how much you can still learn about something every single human being and every single living thing owes its existence to. Imagine it's only been 80 years since we have known how the sun even works. The sun converts 4 billion kilograms of mass into energy every single second. If it wasn't for the fusion process being so slow because of quantum tunneling and the weak force, the sunlight we all know and would have disappeared a very long time ago. Thank you, guys.
Hey guys, I think there are a lot of questions on the chat. So maybe Sagar, Vikrant, Aditya, all of you, could you address some of them? Maybe we can start with Nikhil's question. If one particle gets sucked into a black hole, why does the other particle also not get sucked in? Because both are subjected to the same gravitational field. So can anybody answer this?
Sitara, I think it was already answered by it.
It was answered by Saga?
Yeah.
Okay, what was the answer? I think I missed that. Is he here?
Can you hear me?
Yeah.
Hello?
Yeah, we can hear you.
Okay. So Can you repeat the question again, Cesara, please?
Yeah, so like actually this was a doubt even I had, so I just want to repeat it. Yeah, so there is a matter antimatter pair, right? So how come it is that only one particle gets sucked into the black hole and the other one just escapes? Like
Okay.
why?
So
Yeah, both of them are subjected to the gravitational field. So,
see, actually, there can be three scenarios happening, right? Where both the particles doesn't go inside black hole. They just annihilate and and do the process normally. There can be even this scenario where both the particles are sucked inside black hole, right? Both the particles are sucked inside, and still black hole has to give back the energy back because they can't annihilate and give back the energy. And there
okay.
is a probability that one particle goes inside and one particle stays out. So actually everything is made of probability, right? There is some probability that both stays out, some probability both goes inside, some probability that one goes inside, one goes outside. So I just took the probability where it is somewhat equal to middle of these two, like not too extreme, not too low, but in the middle, where one
Okay,
is
okay. So it's like a statistical probability, basically, of
yeah.
how many of them kind of escape, right? So you answered the next question also. Is it about how can you consider that the black hole is evaporating since one particle goes inside as well, right? So isn't it just a form of radiation then? How can you consider that the black hole is losing mass or energy?
Okay. I think what they meant was if black hole is taking one particle inside, then mass is increasing in black hole, and why the evaporation should happen, right? But actually what is happening is, see, if one particle goes inside, black hole is not keeping that particle, rather it's giving the energy which is equal to the particle, that is mc square. But still, where is that particle going? Is it staying in black hole or is it going somewhere else inside black hole? Now nobody knows what is inside black hole, right? They said that there is in singularity where infinite density is present. But what happens for that particle after it goes to in this singularity? Will it stay in black hole or is there a wormhole that takes it to another universe? So there are so many information, right, which we want to calculate. Like many say that black holes lead to another universe. So that particle would have gone into another universe. And some say that inside singularity they just vanish. So
I think one more I guess postulate from the Hawking radiation thing is that if an antimatter is sucked into the black hole, the antimatter carries I don't know, it has an effect of negative energy. So in some essence it negates the mass of the black hole slowly through the, you know, through the duration of perhaps trillions of years, which is why when all the other stars and all the other objects fade away, black holes will be the last remaining ones and they will also evaporate at some point. But the point is, the evaporation process happens because an antimatter falling into the black hole behaves like, I don't know, negative energy and hence negates the overall mass of the black hole. So it slowly reduces with time. I'm not sure if this is like verified, so we might have to look this up, but I read this recently.
yeah, this is like the information what you know is not the complete information, right? So anything could be possible.
Yeah, also we have never detected Hawking radiation, right? Like just to clear that out. We have never I mean, we know that the theory works really well, but experimentally, I don't think we have ever detected Hawking radiation. Correct me if I'm wrong, but that's essentially why he didn't receive a Nobel Prize for this.
Yeah.
Right.
So next question.
I think they've been having a conversation here, but I think Dinesh asked something. By the way, guys, if you're here on the call, this is a good time for you to unmute and also introduce yourselves and ask a couple of questions that you've been talking about. So, yeah. I think he says, but if the matter goes into the black hole and antimatter goes out in space. Yeah, I was saying if we want to detect Hawking radiation, how would we detect it, and do we have the infrastructure? According to what I know, the Hawking radiation is extremely weak, and I don't think current infrastructure that we have is capable of detecting it. The biggest ways of detecting a black hole, as we all know, is gravitational lensing and the motion of stars around the black hole. But I think it will take many years before we, I guess, detect Hawking radiation.
Yeah. And is Aditya present still?
Who?
Aditya.
Yeah, I think Aditya is still here. No.
Hello.
Yeah.
Yes, so my question is, we know that Roger Penrose and his team detected a black hole. How they can detect it?
So you're telling how black hole was detected. I mean, you mean the first image of black hole?
I think first detection of black hole.
So who asked the question? Can you repeat it again, please?
Hello.
Yeah.
Hello.
Yeah, tell.
Sir, my question is, we know that Roger Penrose and his team detected the black hole. Then, how were they detected? Means, what is the technology and they actually used?
Hmm. Actually, I don't know the correct way because I haven't studied that still. But I think it is due to the, as Aditya said once, the trajectory of stars and the bending of light. By observing that, I think they have gone. I think they have detected, because gravitational lensing is one of the very useful and a very accurate method to find out is there a very large mass present in a particular region. Because if a very large mass like black hole is present, the light what it is being traveled by the stars which are behind black hole. So consider you're in earth and there is a black hole, and behind black hole there are some stars. So now we can't actually see the stars which are behind black hole, but due to the bending of light, the light will be deviated and we actually see that stars and the black hole moves. So this is how I think they find out how black hole is present in that region. And actually this is one of the important tool. Gravitational lensing is an important tool to find out even dark matter in that case. And it's also important to find out many neutron stars, high density objects. I think this is how they have found out detect the first black hole, but I'm not so sure.
Yeah, the only other approach could have been like a long-term analysis of the movement of stars around the black hole. So a lot of times, I guess mapping that data out will give you a lot of information about the mass of the black hole, probably the radius, and so on. So that's another useful way to state that a black hole is there. And in other words, that means we have never exactly detected a black hole by seeing it, right? In fact, the image of the black hole was the first time we have done that. So yeah, it's usually by indirect means. Is Jishnu here? Okay, not yet. One sec. I just want you all to hear from Jishnu for 2-3 minutes, and then we can come back.
So guys, anybody else have any questions? Like, keep it like a discussion, no?
Yeah, you guys can totally unmute if you want to. I think Aruna says if Hawking radiation. Oh, is that an old question? If Hawking radiation could escape the gravity of the black hole itself, does it travel faster than light somehow? I don't think once it is inside the event horizon, it is able to escape, right? So we are talking about particle pairs that kind of spontaneously come into existence outside the event horizon. So yeah, and light can only not escape it if it has already passed the event horizon boundary. Um, yeah. Yeah, Jishnu is here. So Jishnu, we had a question about just how black holes are detected and about the technology that kind of goes into that. So would you like to comment on this?
So I think Jishnu is not there. Did he join?
Yeah, I can actually see him.
Actually, Aruna asked a very good question.
Yeah. Okay, I think he's unable to unmute. Just a second. Oh, he is unmuted. Okay. Can you try saying something, Vishnu? We can't hear you. Okay. Nope.
Can you hear me now?
Yeah, I can hear you. Are you able to hear Jishnu?
No, actually, someone removed me just now. I don't know how.
Oh, okay.
So actually, Aruna asked a very good question. So if Hawking radiation escapes black hole, doesn't it mean Hawking radiation is not attracted? That is, how can it escape? Isn't it, Aruna? If you're still there, I think you can unmute and ask.
Yeah.
I'd like to speak. Hello. Aruna, can you ask the question? Hello.
No, he said he's not able to unmute in the chat.
Okay. Actually, I don't know the correct answer to be sure. So I think Hawking radiation. See, if Hawking radiation is made up of electric and magnetic fields, which we know as light, then it has to follow what light follows, right? If Hawking radiation is made up of electric and magnetic field, then it can't escape. But since it is escaping, I don't think light is a form of electromagnetic wave, because see, Hawking radiation could be anything. It could be a particle coming out, or something pushing the particle outside event horizon, or it could be a gravitational wave also acting as Hawking radiation. And actually, there is a research where they said that Hawking radiation and gravitational waves frequency is matching so much in one of the black hole. I read the research paper. So I think Hawking radiation could be something else, which we don't know its property correctly. So that is why they are escaping from black hole, maybe. I think I've answered it sufficient, but I'm not so sure actually. and I don't like to give wrong information also. So I think Dinesh asked, can anyone please comment on the ADS CFT, that is about the holographic theory of universe? I don't know about holographic theory, but if Kushal or Aditya knows, they can answer. And Nikhil has asked, okay, he actually has answered that. So let's say energy E was used to make the pair. Now each particle would have E by 2